Today we're very pleased to have as our speaker Scott Dodelson from the Evanston-Skokie area, northern suburbs. I just have a few words to say about Scott. Scott is a scientist 3, so this is the highest scientific level in the theoretical astrophysics group at Fermilab. And he's, of course, a professor of astronomy and astrophysics and member of the Academy Institute for Cosmological Physics here at the University of Chicago. Scott got his PhD from Columbia University and had postdoctoral stints at Harvard and at Fermilab before joining the Fermilab scientific staff in 1994. He served as head of the Fermilab theoretical astrophysics group, as have all great cosmologists, and as director of the Fermilab Center for Particle Astrophysics. Nationally, he served on a number of important committees, including the Astronomy and Astrophysics Advisory Committee. He was a senior organizer of the SNOMAS Particle Physics Community Planning Conference that led into the most recent P5 report, which Scott was integral in producing. And most recently, he led the Cosmic Visions Committee, which recommended a number of options for cosmic surveys beyond the next generation of DESI and LSST. He's also a fellow of the American Physical Society. Scott is well known as the author of the best textbook on cosmology called Modern Cosmology, which I'm sure you've all read and worked through all the homework problems. And has a really bewildering array of research accomplishments to his credit. He's really one of the world leaders in cosmology and particle physics. I'll just hit a few highlights so that Scott will have a couple of minutes left for his talk. He in the early 1990s, invented the concept of sterile neutrino dark matter, which is still with us. In the mid-1990s, he was one of the pioneers of studying cosmic microwave background anisotropies in different cosmological models, and ruled out cosmic strings as the origin of cosmological perturbations. In the late 1990s, he used the CMB and other measurements to demonstrate that the universe is spatially flat, which, along with measurements of the low density of matter, provided independent evidence, independent of the supernovae, for dark energy. And more recently, he and collaborators showed how observations of weak lensing and of galaxies can distinguish dark energy from modified gravity models, and that's really driven, and is important in the design of current and future surveys. In addition to his theoretical and phenomenological work, Scott has played leading roles in the analysis of cosmological data. Sorry, this is my daughter. From cosmic microwave background experiments to large-scale structure and weak lensing measurements from the Sloan Digital Sky Survey, to spearheading more recently the joint analysis of the dark energy survey in the South Pole Telescope. In recent years, he recognized the growing need for a real comprehensive analysis framework for cosmic surveys. And so he led the development of what's now called Cosmosis, a framework that's been adopted by DES and will be adopted by LSST, and really, I think, will set the stage for interpretation of cosmic surveys. He co-led the Dark Energy Survey Theory and Combined Probes Working Group and is now co-chair of the DES Science Committee, which is responsible for coordinating all of the science results from DES, so no pressure. Finally, Scott is also well known as a very effective mentor and supervisor of students and postdocs, as many of you know. And many of the people he mentored now have gone on to become colleagues in the field. And he's very well known as a fantastic and eloquent speaker, particularly when people let him speak. So we're very pleased to have him give us his cosmic capstone and Coda of this year-long KICP series on the future of cosmological physics. So please join me in welcoming Scott.
Thanks a lot, Josh, and thanks for asking me to follow up. We heard 8 great talks this year on the future of cosmology, and Michael assigned me the title of Cosmic Coda, which means to wrap it up and try to figure out what these 8 luminous people were telling us about the future of cosmology. So following that musical metaphor, let's do it in 4 movements. And the first movement is clearly the data. What we heard over the past, I guess it's about 8 months or so, is the data are just amazing. Wendy showed us yet another way of getting at measurements of the rate at which the universe is expanding today. Getting error bars on the Hubble constant that are now sub 5%, about the 3% level, and charting out a path to the future which no longer relies on Cepheid, but now relies on population 2 stars. So this is yet another way of calibrating, checking this very all-important measurement that will go down for the next decades or centuries as the hallmark of our time, the measurement of the rate at which the universe is expanding today. Josh put together this graph which shows all the measurements of supernova, type 1a supernova, going out to much larger redshift, past 1, and pointed out that if you average them together and compare the residuals to a model, we get sub% accuracy in the measurement of these distances. So we now have percent level accuracies in cosmological distances, and as you know, the luminosity distance is essentially, actually that's not an equal sign, is it? That is related to an integral of the inverse Hubble constant out to redshift c. That means as we measure these luminosity distances, we can tell not just what Wendy has taught us, how fast the universe is expanding today, but how fast the universe was expanding in the past. Wayne reminded us that it's not just supernova. There is this feature called the baryonic acoustic oscillations that's present in the distribution of galaxies. We know the physical size of this feature, so when we observe how big it appears on the sky, we can infer the angular diameter distance out to those objects. And we now have measurements, current measurements, depicted by these symbols here, that are roughly at the 10% level. And we have aims to get, even with the current generation, with EBOS, of getting down to the 3 or 4% level. And again, we hope to get to the percent level with these baryonic acoustic oscillation measurements all the way out past redshift 2. Wayne also reminded us, as did Andre, that we are beginning the historic journey of measuring the rate of the growth of cosmic structure. So this is, again, something that we will leave for future generations. Currently, we have kind of 20-ish% measurements as a function of redshift of how the clustering amplitude evolves with redshift, but we have a comprehensive program of multi-wavelength probes to be able to chart out how rapidly the structure in the universe is evolving with time. And then there's a microwave background. Michael pointed out that over April 1992, Kobe first reported anisotropies in the temperature of the microwave background, and since then the satellites WMAP and Planck, and of course the ground-based experiments, have provided ever better resolution and sensitivity, so that we now have these exquisite maps of the cosmic microwave background. What the universe looked like when it was only 400,000 years old. John Karlstrom not only did this, but showed us that you can take the spectrum of those maps, you get this exquisite series of peaks and troughs that we expect, because we know that when the universe is 400,000 years old, the electrons and protons were not in the form of neutral hydrogen. They were tightly coupled to one another and to the photons. So they formed a fluid, and if you had an overdense region here, the pressure of the photons drove the overdensity to be underdense. So there was this restoring force of pressure, just like you have a restoring force with the guitar string. So just like with the guitar string, you get a fundamental frequency and a series of higher harmonics. So too with microwave background, you get a fundamental frequency that teaches us about the sound horizon, and you get these higher harmonics that in music enable us to distinguish between drums and pianos, and in cosmology enable us to learn about the constituents of the universe. And if you count carefully, John and his colleagues have now measured 8 or 9 of these acoustic peaks. Again, this is a signature achievement. This will go on, last for decades, centuries, millennia. It's not only the temperature. Daisy first measured, again, John and his group, first measured the spectrum of CMB polarization, detected at 5 sigma. We now have measurements of the spectrum of the polarization out to very high multiples, out to very small scales. It's the amplitude's a factor of 10 smaller, as predicted. The phase, they're out of phase with the temperature anisotropy, as predicted. And we see the march of this progress. First detected at 5 sigma 15 years ago, and now we have this plot, which is only going to get more and more precise. The microwave background not only gives us a pristine view of the universe when it was very young, but there are also secondary anisotropies. And it used to be we used these secondary anisotropies to supplement optical observations. We found galaxy clusters, and then we looked at them to try to see how the photons in the microwave background were upscattered by the hot electrons in the cluster, the so-called Samuel-Dovich effect. John and his colleagues have perfected this technique not only to study detected clusters, but to detect clusters themselves. So whereas before we could only detect optical clusters or X-ray clusters out to redshift a half or so, SPT, for example, has measured hundreds and hundreds of clusters way past redshift 1. That's one secondary anisotropy. The other secondary anisotropy, and just have to pause to brag here about Chicago, Wayne developed this formalism 15 years ago. This map was constructed using data built by many people in the room. Out. The analysis was spearheaded by Gil Holder, a former student here, and this is a 2,500 square degree map of the mass. We're used to seeing in astronomy maps of galaxies of light. This is a map of the mass. It's a remarkable achievement, and again, this is something that's exploded in the last 5 years, from 2, 3, 4 sigma detection in 2011 to what we currently have with SPT and Planck. Really remarkable maps of the mass integrated along the line of sight. Josh not only does good introductions, he also has great foresight. So he realized 15 years ago that since SPT will be built in the south, it makes sense to build an optical survey there as well. This is the mass map provided by SPT in the south. DES now has data that overlaps that same region. And surprise, surprise, the mass that produces the lensing that Wayne taught us how to detect, that lensing is produced by mass that's associated with galaxies in DS. You can actually see by eye the correlations between the hot spots in the mass and the galaxy maps, and the cold spots. Angela reminded us that the microwave background does one other thing. That is, when you have very, very high energy cosmic rays, the highest energy cosmic rays you can imagine, the microwave background absorbs them and rescatters them. So there should be this so-called GCK cutoff, and Angela and her colleagues have led the way in discovering the GCK cutoff. Josh reminded us that the dark energy survey has also been able to double the amount of nearby galaxies we see, small galaxies we see in our local neighborhood, and these serve as sites where we might look for dark matter. So within the past 2 years, the number of satellite dwarf galaxies has expanded by a factor of 2, thanks to the dark energy survey. This too was driven by Keith Bechtold and Alex Turbo. And then Andre taught us about the power of simulation, to not only find in simulations this incredible feature of a splashback radius, but to go out, he and his colleague went out and found this splashback radius in Sloan's digital skies survey data. And as we speak, there are emails going around looking for such things in the dark energy survey. So this is a triumph of simulations coupled with data. And Rocky reminded us that there are a host of other observations, such as galaxy rotation curves, gravitational lensing, rebading nucleosynthesis, and cluster collisions, all of which bewilder us, because none of this can be explained with the ordinary matter in the standard model of physics. Second movement. We have a model that explains all of this data. So Rocky put together this suite of observations that cannot be explained without introducing dark matter. Let me just focus on one of them, structure formation, because that's something that Andre also touched on as well. And I venture to guess, Andre's not here, but I venture to guess, I can say if he's not here, that he's, oh yeah, okay. So he's in the back. That was the thing. I would bet that Andre has never run a cosmological simulation without dark matter. And I'm not saying anything, so let's say that's true. That means there's no way of understanding how structure forms in the universe without dark matter. So I'd like to try to explain why I think that's true. So the maps in the microwave background are uniform to one part in about 10,000. That means there might be a small inhomogeneity, but if there are 10,000 protons here, there are 9,999 there. And there's no greater inhomogeneity than that. Today, as measured by DGS or the fact that we exist, the density in this room is 30 orders of magnitude larger than it is in the normal place in the universe. So the universe is very nonlinear today. How did it get to go from there to there? So what we believe is that those small inhomogeneities, there are more people in the back of the room than in the front of the room, so over the course of 14 billion years, people in the front of the room will migrate to the back of the room, and those small inhomogeneities will grow to be these huge nonlinear structures, clusters, filaments, galaxies, that give rise to stars and planets and us. So it's a beautiful picture that the small inhomogeneities grew to be the nonlinear structure we see today. The problem is it doesn't work. So you can apply general relativity theory of gravity to this map of the microwave vacuum. You know the level of inhomogeneities in this map, 1 part in 10,000. And what you find is that they should have grown in amplitude by a factor of 1,000 since this time. 1,000 would bring them up to 10%. So this is not a 5 sigma experiment or discovery or detection. This is a, we would not be here to talk about it, observation. That is, if the inhomogeneities were at 10%, the universe would never have gone nonlinear, and we wouldn't be here. So this is a, without dark matter, there's simply no way to explain how the universe became nonlinear. And the simplest interpretation is one that was invoked for completely different reasons. That is, you invoke the idea that there's dark matter that's not captured in these maps. And the inhomogeneities in the dark matter are actually much larger than those that are captured in these maps. And those indeed do grow by a factor of 1,000 from this time into today, and they do indeed enable the universe to go nonlinear. So we quantify this with the power spectrum as a function of scale, large scale, small scales. This is the data. On large scales, this dimensionless combination of the power spectrum, if it's less than 1, the universe is linear. If it's greater than 1, it's nonlinear. On large scales, the universe is linear, it's relatively smooth. So if you drew big spheres on the sky of 30 megaparsecs, those big spheres would all have the same, roughly the same number of galaxies in them. But on small scales, the universe has indeed gone nonlinear, as a model with dark matter, as depicted by this solid curve, can reproduce. If you did not have dark matter, then you would have fluctuations at the 10% level, is the square of the fluctuations. So you would not have galaxies, you would not have, and you would not have us. So dark matter is necessary in order to understand the structure of the universe. So Andre, I claim, has never run a simulation without dark matter in it. It's not true. Okay. Rocky pointed out that there are 3 ways of detecting dark matter. We can look at them accelerators. We can take 2 normal particles, collide them together, and produce dark matter pairs. We can have the 2 dark matter, that's directly into the LHC. We can have indirect detection where 2 dark matter particles in space annihilate and produce normal stuff that we see. Or we can have 1-on-1. We can have a dark matter particle hit an underground regular particle and observe the nuclear recoil. That's called direct detection. So we have these 3 different ways of getting at dark matter. And as Rocky constantly reminds us, this will be probed over the coming decade. And we said that for decades. The second class of measurements that cannot be explained by ordinary matter are the distance measurements that Wayne and Josh and Wendy talked about. So the salt barometer likes to place these distance measurements on this graph. I quite like this, so let me just walk you through this. This is reversing the axes. So usually we're used to putting distance on the y-axis and redshift on the x-axis. Salt points out that you can do the opposite. You can put redshift on the y-axis. In this case, it's not redshift, it's scale factor, which is, A is 1 over 1+c. So today is 1.
Hubble do that too?
Could be. He left out, Hubble's thing, the plot that I'm familiar with, is, has velocity on the y-axis without a 100%. Anyway, so this is the scale factor. So it was, if the universe is expanding, it was small early on, and today it's 1, normalized to 1. And it essentially quantifies the distance between objects. And on the x-axis, instead of putting distance, the distance to an object, you put essentially the look-back time to that object, the time it took the light to travel from that object to us. So as you go back in time, the universe was indeed small, the universe is expanding. What you kind of expect is that the universe should be decelerated. That is, the points were over here, and then this expansion rate is slowing down. Expect that for a reason I'll get to on the next slide. You expect something like that. Instead, you see something like this. The expansion rate is speeding up. So it's very clear in this plot to see by eye that the universe is accelerating. And that's not what we expect. So here is the fundamental action that explains the world. There's the Einstein-Hilbert action and gravity coupled to all of matter. What Einstein taught us is that this describes the geometry of a system. This describes the energy of the system. If you minimize that action, you get Einstein's equations. If you apply those equations to the universe at large, you get the Friedmann equation, which relates the expansion rate to the gravitational potential energy. But think about it. You're locked in this room for the next hour. The number of atoms in this room is not going to change. If the room doubled in size, the volume would go up by a factor of 8. The density would go down by a factor of 8. So as the universe expands, we expect the density to go down as the volume, or as this scale factor, A cubed. So this combination here should go down as the universe expands. And therefore, the expansion rate, the rate at which dA dt, the scale factor is changing, should be going down. The universe should be decelerating with time. Instead, the universe is accelerating. So some fixes. One possibility is that there's vacuum energy, so-called cosmological constant. That kind of makes sense. That is, as the universe expands, the density is not going down. It's got to remain roughly constant. And the only way to get that to happen is to have there to be energy associated with empty space. That's a possibility. Another possibility is that energy is zero for some reason we don't understand, but there's some additional quintessence or dark energy that drives the acceleration. Or another possibility is that this equation is wrong, and Einstein was wrong. We have to modify gravity. Virtually all of these solutions require, in the fundamental Lagrangian, a new dimensional constant, and that constant with dimensions of mass is typically incredibly small. It's in the order of 10 to the minus 33 electron volts. Contrast that with the smallest mass in physics we know about, which is about 10 to the minus 3 electron volts or so, and you have a huge problem. So however you decide to solve this problem, we have a huge challenge on our hands in incorporating that into the rest of physics. And that is indeed the motivation for the Dark Energy Survey and the South Pole Telescope. And as we've seen, there are ways in which they synergize that we didn't even imagine at the beginning. And what we hope is over the coming years, we'll learn something about this phenomenon of dark energy, or whatever it is that's driving the current epoch of acceleration. Microwave background. On the one hand, it's simple. You take a simple note, and you take the spectrum of that note, and you have a fundamental frequency and the higher harmonics. And that's exactly what you get in the CMB. It's exactly the same physics. Acoustic oscillations, you should get the same thing. So why do I say that you need new physics in order to understand it? So it's kind of a subtle argument that's going to take most of the rest of the second movement. All the rest of the second movement. So you know the argument, open your laptop. If you don't know the argument. So this is it's a subtle argument. Okay, so here it goes. The microwave background is different than a musical instrument. There are two trivial differences. One is the spectrum that John and colleagues produce is a Fourier transform of a spatial, not a temporal signal. Our ear does the Fourier transform of a spatial, of a temporal thing. That's trivial. The time scales are slightly different. That's trivial. The difference, though, is one key difference is that the reason why you get those peaks and troughs in a musical instrument is the ends are tied down, right? So only certain frequencies are allowed, and certain are not. Whereas in the microwave background, all possible perturbation, all possible wavelengths are allowed. So why is it that we only observe some? There are this coherent series of peaks and troughs. So the answer is one of timing. Here's a plot of the amplitude of different Fourier modes as a function of time.
Remember, we observed these modes when the universe is 400,000 years old. So a large-scale mode has a wavelength so large that physics really can't affect it at all. So it remains roughly constant over the course of time. So its amplitude, we observe it as having maximal amplitude and when, at recombination. A slightly smaller scale mode begins its acoustic oscillations and has undergone half of an oscillation. So this mode has also a maximal amplitude when we observe it. This is the mode associated with the first peak. A slightly smaller scale mode, the so-called Jeb Bush mode, goes through 3/4 of an oscillation. So this mode peaks very early, but it peaks too early. And then its amplitude at recombination vanishes. So we see it as a trough in the microwave background. I used Hillary that's not true. Anyway, so that's true. And then if you go to smaller scale modes, that's undergone a full oscillation. So we see that mode as the second peak. So on the one hand, it's not an exact analogy with the musical instrument. On the other hand, it's a boundary condition and it's a question of time. There's another subtlety hidden in there, though, and that is a given wavelength perturbation. A given wavelength, there are many different modes, since we live in a 3D universe, that have the same wavelength. So these two modes have the same wavelength. And when you combine them, you get something like this. And then you can add in a third mode that has the same wavelength, just oriented differently, right? So these are this is in 2D. You can imagine 3D is even more, right? And you combine it, and you start to get a picture of the sky. So you get, in order to get to, so in this case, I've combined 3 modes with the same identical wavelength. So the spectrum of this universe looks like this, it's just a delta function, right? There's only power at one frequency. More generally, what we're doing at every single frequency, at every single L, is we're combining many different Fourier modes with the same wavelength. Some oriented like this, some like this, some like this, right? We have to combine all of those modes. And that raises the question, why are all of those modes in phase? Let me show you what I mean. I showed you before this red mode, this first peak mode, and I implicitly assume that it started off with 0 velocity. But that, since we're averaging over an infinite number of modes with the same wavelength, I implicitly assume that all of these modes start with the same exact phase. They can have different amplitudes, but the point is they all have their maximal amplitude when we observe them. And similarly with this Jeb Bush mode, you have this thing that's 0, but that assumes that the velocity initially was 0, and you have to assume that all of those modes with the same wavelength start with the exact same phase with 0 velocity, and then they do indeed lead to a first trough. If I have not made that assumption, if I just allowed them to have random velocity starting in, then I would have the same exact amplitude at the first peak as at the first trough, without just white noise. So the fact that there are these series of peaks and troughs, is a mystery. It requires synchronization of the phases at early times. And it's actually a deeper problem than that. This is a plot of time, distance, kind of on the perimeter. So the red shaded region here shows the distance that light has traveled, could have traveled since the beginning of time. And this is the wavelength of a typical Fourier mode measured by the CMB. So as you go back in time, the wavelength of this mode is larger than the distance likely to travel. So the question is, what could have synchronized this mode? What causally, this mode is not in causal contact with it. Its wavelength is so big that causal physics can't impact it. So how could its phase have been set by some causal process? Doesn't make any sense. So the solution to this is to invoke the idea that very early on, there was an epoch of accelerated expansion called inflation. And that really all of these modes were in causal contact with one another. Their wavelength became very large, they so-called left the horizon. And during this time when they left the horizon, their amplitude was constant. And then they came back in the horizon with this constant amplitude with 0 velocity. So that means in this picture, what happens is you have these quantum mechanical fluctuations during inflation. The modes left was stretched over past the horizon, they remained constant, and they re-entered the horizon with this constant phase. So that's the reason for the synchronization. Inflation provides a reason how these phases were synchronized. And that's the reason why we see this exquisite structure of peaks and troughs in the microwave background. It all traces back to this period of accelerated expansion in the early universe. So what this requires, though, is yet another epoch of acceleration. So we need another epoch very early on, during which there was some form of dark energy, or whatever you want, that led to this accelerated expansion. That's the only way to explain this coherent series of peaks and troughs that we observe. And that's one of the missions for all of us, is to try to figure out what drove inflation, and the way we think the best way to do it is to start looking for the gravitational waves that were produced during inflation by looking for their signature in the polarization of the microwave background. John and his colleagues have started to do that, and we're very excited about the coming decade where we have more and more powerful instruments to come online to eventually measure these B modes in the same depolarization. Third movement. So the consensus model then that explains all this amazing data is built on these three ideas, which are really new physics. We're making it up. We're saying there's dark matter, never been found. Dark energy, never been found. Inflation, we just made it all. So the cosmology works great, but it's really incumbent upon us to find new physics. By the way, that's a great thing, because we're looking for new physics. We've been searching for 40 years for new physics beyond the standard model. And what cosmology tells us, there is new physics. It's the only way to explain the data. And now it's up to us to find new physics. Third movement. Hidden in the 8 talks we heard, I believe, were 2 messages, hidden messages. So these are messages that I think we heard from everybody. Michael showed pictures of people. Showed pictures of Hubble and Dave Strand and Wendy. Wendy showed lots of pictures, just one of them. Pictures of people who've been part of Chicago for many, many years. Angela showed lots and lots of pictures of people. There's just one, she showed almost everyone in the room, basically. There's just one of her slides with lots and lots of pictures. John showed pictures, I keep on mentioning his name, but as he would readily admit, it's literally 50 people who have contributed to the success of the South Pole Telescope. Rocky showed pictures. Wayne showed pictures of people. Back to normal. Josh showed pictures of people. He showed pictures of, and these again, just a subset of many pictures of people who have contributed to optical astronomy at Chicago. And Andre showed many, many pictures of many, many people who have wandered through these halls and contributed to the science. So what's the meaning what's the hidden message that they're all trying to tell us with these pictures of people? So if you're like me, this reminds you of this graph. This is a plot of the number of Christians as a function of time. Starting in the year 0, we were at 0 then, and moving into the year 350. So this is actually a model, but it's probably projected in this. But we actually know the endpoints fairly well, right? We know how many there were in year 0. And we know that by the time of Constantine, there were 10 million or more. So the number of Christians went from 0 to tens of % of the whole world population in just a few hundred years. How did that happen? Why and how did Christianity grow so rapidly? So one possibility that modern scholars have proposed is it was the people. Christianity actually was a much more welcoming society for women. Women did much better under Christianity than under paganism or under Christian Roman neighbors. The family structure was much more stable, according to modern scholars. Looks like Craig disagrees with the books that I've read. There were martyrs who gave their lives for the faith, and that inspired millions of people to join onto the cause. And it wasn't just these soft things that they did. The claim, here's a quote from Dionysius from the year 260. This is 9 years after the Antonine plague. This was probably a measles plague. There was another plague in the year 180, probably smallpox, that wiped out roughly 30% of the world population. So what Dionysius said is, I'm not quoting the bad things he said about the pagans, but what he said about the Christians was, heedless of danger, they took charge of the sick, attending to their every need. And Stark and others claimed that this sense of Christian morality actually not only was good for recruiting, but it saved lives. That it helped their population remain relatively stable and suffer fewer losses through these plagues. So one possibility for the rise of Christianity, before by modern scholars, maybe not all scholars, is that it was the people. Got through that one. Okay. So here too, it's the people. Just forget about everyone else. Just look at the 8 people who have presented to you. Michael and Rocky are not here, so I can say they founded the field that combined particle physics and astronomy into this field of cosmology and taught us that the large is connected to the small. They literally founded that field. Wendy Friedman, she is the one person most associated with measuring the Hubble constant. As I mentioned, in 10, 100, 1,000 years, her name will still be recognized as someone who gave us that. John Carlstrom, same thing, microwave background. Angela Linton, unprecedented in breadth. Started out doing cosmology, neutron stars, and now she moves on to the Auger experiment and measures the GZK cutoff. Wayne Hu is the one person I've learned the most about cosmology from simply by reading his papers. Andre has taught us more about the distribution of dark matter in the universe than anybody. And Josh not only was one of the first to recognize the existence of dark energy, but has led and initiated the major surveys that are designed to detect it. So these people are literally here in our building every day. When you walk to work every day, you should say, wow, Wendy Friedman is right there. So you should be really, first of all, you should bug them. They have a lot of wisdom. And second of all, we should be appreciative of the fact that we're in a building with these people. So it is the people. And it's not that they're great scientists, they're good people. So we all have dozens of stories. I'll just share one. About 5 years ago, Bruce Winstein and I were going through medical things. His was major, mine was minor. So we both had MRIs. So here's an excerpt from Bruce's email to me. This is my first MRI. I concentrated on the music generated by the pattern of changing magnetic fields. It was really not unlike some electronic music that I used to listen to. When I finished the scan, I mentioned this to the tech, who said that a French lady musician patient had come back with the recording crew and made a little video about it from the electronic music side of things. So the thing I love about this is the optimism and the serenity, and what's not here is the support that he gave me. I had surgery a month or so before. And note the date, January 19, 2011. Unfortunately, Bruce passed away the following month. We went down to Washington, D.C. in June of that, 4 months later, 5 months later, and Michael, who's very inspirational, just had to say one sentence, which was, let's do it for Bruce. So it's people like Bruce and Dave Schramm and all the people who Angela and Wayne and Josh showed us, their legacy lives on. They've said things that have been passed on that really contribute, even if you never met them, they contribute to the work that you and we are doing. So I think you should appreciate that. The second hidden message. Did you buy the first one? Okay, the second hidden message. So here I'm going to delve into religion. I know a little more of that. So Craig's not okay. The tension. Many of them mentioned tension. Wendy showed this plot of the tension between measurements of the Hubble constant by the CMB and the local measurements of Hubble constant. Wayne showed us this plot, which shows the tension in measurements of sigma 8, as inferred by clusters and CMB and Dodelson. Josh, on his last slide, said the multiplicity of high-precision experiments and probes suggests there will be a number of tensions to resolve due to systematics and or departures from lambda CDM. And Michael talked about it not in terms of the tension of the cracking of the cosmic egg, talking about anomalies, again, these tensions between hadrons, sigma 8, the low L anomalies. So this constant focus on the tension, Well, what's the reason for that? Why is the excitement that I was gleaning from these talks about the tension even more so than finding new physics? It seemed like the tension was the big thing. Okay, same time period, different religion. Here is, this is one page from the Babylonian Talmud. And so some of your Aramaic is a little rusty, you can tell some of the root. So this is, every religion has to grapple with the question of, does bad things happen to good people? So in Judaism, the way that discussion is framed was established on this page, in this shaped thing, by a guy named Jacob. And this guy was not one of the elite scholars at the time. He was kind of like a little bit, kind of a part of a graduate student, think of it like that. So he wasn't, I think in the 2,800 pages of Talmud, this might be the only time he's mentioned. So this is what he says. He says, okay, they're talking about reward and punishment. He says, you want to talk about reward and punishment? There are actually only 2 times in the Bible. So he knew the text, and he's like a graduate student who had passed the candidacy exam. He knew all the text. So he knew there were 2 times in the Bible where reward for something you did is mentioned. One is when you honor your mother and your father, that's one. And the other is when you do this obscure commandment, that if you want to get the eggs from a nest, what you're supposed to do is first chase away the mother bird. It's supposed to be a compassionate thing to do. It's a commandment to first chase away the mother bird and then get the eggs. So for some reason, in that commandment as well, it's stated that if you do that, you'll live a long and good life. So this guy knew those 2 facts. He knew the literature, so to speak. He passed the candidacy exam. And he made the following observation. He said, I saw the following thing happen. I saw a boy. His father said to him, go up to the roof and bring me those eggs. So the boy went up to the roof, he climbed the ladder, went up to this rooftop thing. He brought the eggs, and then he sent away the mother bird. And then he took the baby eggs, and then he came back down the ladder and fell down and died. Right? So he said, basically what is he saying? He's saying, okay, all you scholars, right, I get it, you believe in reward and punishment and stuff like that. And you can make excuses, that, okay, maybe you don't get rewarded today, you get rewarded in 10 years. But here's an explicit example, and by the way, it tells you something we all know. There's no reward and punishment for things you do good. It just doesn't work like that. So this statement by someone who's not one of the leading scholars, I think is, to me, it's a great message that it's encoded in the whole book. And this is the framework for the last 2,000 years, for at least my religion, to discuss this question. So I think a healthy intellectual environment thrives on young people not reproducing what their elders tell them to do, but uncovering hidden assumptions and proving everyone wrong. I think that's what this message tells me, and I think that's what all of the prestigious speakers are trying to tell us. That it's up to you, the young people, to uncover the hidden assumptions that have gone into this model and figure out, don't do it like a crackpot, read the books, be familiar with the literature, pass the candidacy exam, but figure out where we're wrong. I mean, do you really believe this? Figure out where we're wrong. Just figure out, we must be missing something big. Just like, the guy said, fell down the ladder, he died. There's no way getting out. We're missing something big. Figure it out. Okay. Got through those 2 religious things. 4th movement, future. My German is not as good as my Aramaic, but this is the interpretation I found. This has all been Beethoven's 9th Symphony, and so this is the 4th thing. And as I understand it, the words can be translated as, "Oh friends, not these tones. Let us raise our voices in more pleasing and more joyful sounds." So with that in mind, the future is obvious. It's just the work that the people in the back, the graduate students are doing. So I want to walk through, in just a few minutes, some of the work that the graduate students are doing to the accompaniment of Beethoven's 9th Symphonies. So this is actually not all the graduate students, not all their work. But it is the work that was represented in the posters. Ross Coffin is asking the question, how can we extract the most information from photometric surveys? Can we constrain photometric redshifts using galaxy clustering and CMB lensing? So Ross has been one of the leaders in combining DES and SPT data, and what he's found out is that you can constrain using galaxy clustering, and the mass math from, for example, SPT with galaxy clustering, you constrain the properties of the photometric redshift distribution of DES. And believe me, Josh gave me all this responsibility and DS to make things happen. This photometric redshift stuff is one of the most challenging things we face, so Ross's work is very important. Chen He has been working with Wayne to ask, what was the physics that drove inflation? And in particular, we know for the most part the perturbations that were responsible for the stuff we see today were adiabatic, but there might have been isocurvature perturbations. And if there were, that would speak to the underlying physics. So Chen has worked on very sophisticated techniques for extracting those small signals from the CMB. Brittany Kamai has worked on very important questions. What is the very profound question? What is the nature of space and time? And in particular, how sensitive an interferometer can we build to help us find out? The kilometer probes frequencies not probed by any other instrument. James Lasker is interested in the question of what is dark energy, what is driving the current epoch of acceleration. That's very interesting. Can DES, for example, distinguish? So DES is a photometric survey, so we can detect supernova, but it's difficult to classify them. And a key question is when we use them for distance measurements, can we distinguish the core collapse supernova from the type 1a supernova that give us the distance measurements? So James has worked with Dan Skolnick and with Rick Kessler and with Josh and with others to try to figure out how that contamination of the core collapse supernova will impact our measurement and our interpretation of what is driving the current epoch of acceleration. Phil Mansfield has worked on the very interesting question of what is the best way to store information in cosmological simulations. He has come up with an algorithm to reduce by a factor of 10 the storage requirements, and that has dramatic implications for how we will work in cosmic surveys. And he's also worked to understand what is the most accurate way to measure the splashback radius in simulations. Alessandro Manzati's worked with me, it's been a pleasure, and he and I have been asking the question, what external observations will help CMDS4? So this plot shows if you get external priors on other parameters, how well will you be able to determine the sum of the neutrino masses? So in particular, if you get an external prior on the Hubble constant, as Wendy and colleagues might, push that down, you get better and better constraints on the sum of the neutrino masses. And remember, we know that the neutrino masses have to sum to be greater than 60 millielectron volts. So if we get down to here, that's already a 3 sigma detection. So that would be great using these external measurements. Pavel Matlock has worked on two kind of different things. So he's worked on the most theoretical question, what is driving the current epoch of acceleration if you don't forget about dark energy, try to modify gravity? And he's found that it's very, very difficult. He's in particular focused on, one of the questions he's focused on is, do theories of massive gravity lead to superluminal propagation, which would render them inconsistent? At the same time, he's also been trying to figure out if you can detect high energy neutrinos by observing radiation emitted by showers that propagate through ice. Talk about graph. Zodi Pan has worked with SPT. He's interested in the question of can we produce these gravitational waves produced at the earliest moments of time. And in particular, he's focused on the response of these amazing TES bolometers that SPT has produced and all the electronics that surround them in these, there are 277 of these things, that will go on SPT3G. How amazing can we make the SPT3G detectors? Jason Coe has worked on what is driving the current epoch of acceleration. Can strong lenses in DS help us find out? He's also worked with me on really interesting my great background. The Cosmic Coda, what have we learned from these now it's been 9 talks? The data is amazing, unprecedented amount of high quality data inform us about the cosmos. We have a standard model of cosmology that explains virtually all the data and requires new physics. It's finding new physics. There are hidden messages in the talks that we've heard. I would say they are appreciate the people here and work hard to show they are wrong. And from the final thing to the faculty, I'll tell you that from interacting with the graduate students, what we've seen, the future looks very bright. Thank you very much.
Led Zeppelin. So we have time for some questions, and I guess I'll try to pass the microphone around.
I just have a comment. I mean, you listed so many things for Scott's in Scott's paper. There's almost nothing left to add. But I was very impressed, Scott, by the fact that you showed the Aramaic text in Hebrew scripture, and you actually read it from right to left in real time. So it was obvious that you understood everything that you were saying. I was immensely impressed.
Any other comments? Questions?
I thought very simple. I don't know if it's covered, it's so trivial. I thought dark energy included that. Is that
Yeah, that's fair.
And cosmological constant, you didn't mention it, that might be.
Right, dark energy is a principle, a class of solutions that includes, so the question, it's raising a broader question that I actually asked Wayne, and I talked about today to a visitor from Oxford. Anyway, the question is, so to agree, let's call dark energy and cosmological constant one class of solutions. Is modified gravity a different class or not? That is, can you distinguish theoretically between modified gravity and dark energy? And I think some people in the field are not so sure, but it's kind of an interesting question. Because in each case, there are extra, except for the cosmological constant case, there are extra degrees of freedom. So the question is there a qualitative difference between those two things? I'm not sure really.
Andre wants to talk about this dark matter.
Yeah, but I don't think I've never done a non-technology.
Sorry, can you say
I've
that?
never done a non-technology simulation, but other people have.
Well, I was talking about you.
Yeah, so I don't see any reason to do a non-technology simulation. But my question is, so you talked about tensions as a way, sort of very important message that provides the way forward. But I wonder if you can make a few comments about questions of different kind of tensions, which are usually described as fine-tuning problems. So the fine-tuning problems that existed in the late 1970s, but with inflation and very productive. But we still have certain fine-tuning issues like why we're getting just so close to when acceleration started, and stuff like that. So do you think that this is a productive area of solve that includes future sessions beyond people? As example, one of the things that it should be sort of probing.
Yeah, I mean, there are interesting coincidences. We seem to be living in a special time when the cosmological constant is just kicking in. That's a potential coincidence. There is a coincidence between the neutrino energy scale and the cosmological constant, like energy density scale. That's a potential thing that you might be interested in. There's in modified gravity models that purport to explain the acceleration, and those that purport to explain the anomalies associated with dark matter, there are two coincidences. One is they both introduce a mass parameter in Lagrangian that is 10 to minus 33 eV, that is Mond and all modified gravity models for acceleration. And two, the Teves model of Bekenstein resolves the growth of structure problem even without dark matter. So that's kind of a suggestion that maybe modifying gravity makes sense. But it's slim picking. So it's difficult to know. We have to develop our intuition and figure out where we want to head. Personally, I spent a couple of years trying to learn Mond and Teves. I found that really fun. But I'm not sure I'd recommend anyone else do it. But but yeah, I would recommend, if you ask me my advice, read Stephen Weinberg's article on cosmological constant. Read a paper by Pavel Krupa, who's probably, he's being recorded, who's outside the mainstream, but he's provocative. Read something provocative and figure out whether it makes sense. Read something outside your field. Read a technical definition of naturalness as given by the particle physicists and see whether the things that Andre just alluded to, whether they fall into that category or not. Spend half a year trying to figure out what, how field theory how effective field theory affects dark energy. I mean, I don't know. Do what you want. Yeah.
Are you talking to your kids there? Or?
Yeah. They don't know.
Other questions? Sorry.
It's good incentive to ask more questions.
So the 2020 seems very bright for cosmology. We have W focus, LSST, and other probes. But when should we, the young people, should start thinking about the 2030s? Making like what would be the new observations and start planning on that new decade, or everything will just be measured and we just have to change fields?
That is a great question, and there's a definite answer. September 22nd and 23rd, KICP will be hosting a workshop on future surveys for the 2030s. So the registration days will be tomorrow. I'm serious. And that overlaps, as I'm saying, with the workshop, the first 2 days on CMBS4, Monday and Tuesday. And there'll be an overlap day, Wednesday, the 21st, that where we'll discuss cross-correlation, which is, as you know, emerging as a very exciting field. So the third week in September is the time to start thinking about that.
Other questions, comments? No? Okay, well, I think we have a reception outside, and let's thank Scott again.